The interval segment tree module provides range query and update operations over ordered numeric intervals. This implementation maintains a balanced binary tree structure where each node stores aggregated interval data. The tree is initialized with a specified capacity and balanced factor. Queries execute in logarithmic time relative to the tree height. Updates similarly propagate through the tree structure without requiring full reconstruction. The module supports integer and floating point interval endpoints. Node structure consists of a left interval boundary, a right interval boundary, an aggregated value field, and pointers to child nodes. Leaf nodes represent individual intervals at the finest granularity specified during tree construction. Internal nodes merge the aggregated data from their children using a specified reduction function. Memory is allocated contiguously, where possible to reduce cache misses during traversal. The tree maintains a height invariant ensuring no path exceeds log base 2 of the node count. Construction begins by supplying the total interval span as minimum and maximum bounds. The builder accepts an optional leaf node count parameter, which defaults to the next power of 2 greater than or equal to the specified value. During initialization, leaf nodes are created first and populated with 0 or default values. Internal nodes are then constructed bottom-up, computing aggregated values from child contributions. The tree becomes immediately queryable after construction completes without additional warm-up phases. Range query operations specify a query interval with inclusive lower and upper bounds. The traversal algorithm begins at the root and recursively descends through child nodes. Nodes completely contained within the query range contribute their aggregated values to the result. Nodes partially overlapping the query range require recursive visitation of their children. Nodes completely outside the query range are skipped entirely. Query termination occurs when the traversal has visited all relevant nodes or reached leaf level. Point update operations modify a single interval within the tree. The update operation first locates the leaf node corresponding to the specified interval boundary. Once the leaf is located, the new value is written to its aggregated field. The update then propagates upward through the tree, recomputing parent aggregates using the reduction function. The propagation continues until the root node is reached. All ancestors of the modified leaf receive updated aggregate values. Range update operations apply a modification to all intervals within a specified boundary range. Lazy propagation is supported through an optional deferred update mechanism. When lazy propagation is disabled, updates execute immediately and propagate values upward as described in point updates. When enabled, update requests are stored as deferred operations on internal nodes. Child nodes receive the deferred update only when subsequently accessed. This reduces write overhead for large contiguous range modifications. The reduction function is a use-supplied callable that combines values from child nodes into parent aggregates. Common reduction functions include summation for accumulative metrics, maximum or minimum for boundary tracking, or custom domain-specific operations. The function must be associative and commutative to ensure consistent results regardless of visitation order. The function receives 2 child values and returns a single combined value. Identity values must be specified for initialization of nodes without child contributions. Memory management follows a fixed allocation pattern determined at construction time. The total node count is pre-computed based on the tree structure. Nodes are allocated in a single contiguous block or in smaller segments depending on the platform memory model. The allocation is explicit and removes all nodes and their associated metadata. The module does not support dynamic resizing after construction. Constructing a new tree with different capacity is the recommended approach for capacity changes. Tree traversal maintains a visited node counter to track algorithmic complexity. Query operations record the number of nodes examined. Update operations record the number of nodes modified. These statistics are available through the statistics interface after operations complete. Monitoring traversal depth helps identify tree balance issues. Exceptionally deep traversals may indicate unbalanced construction or data that violates construction assumptions. Rebalancing is not automatic and requires reconstructing the tree. Serialization support is available for persisting tree state to external storage. The serialization format includes tree structure metadata, node layout information, and aggregated values. Deserialization reconstructs the tree from stored format. The serialized representation is not human-readable, but is compact and optimized for rapid restoration. Serialization preserves deferred updates if lazy propagation is enabled. Cross-version compatibility is not guaranteed and requires matching software versions for deserialization. Boundary condition handling specifies behavior at interval endpoints. Queries using strict inequality bounds exclude the boundary values themselves. Queries using inclusive bounds include boundary values and results. Updates respect the same boundary specifications. Floating point intervals handle precision carefully. Small epsilon values prevent boundary misalignment issues. The default epsilon is machine epsilon multiplied by the interval span. Specification of custom epsilon values is available through construction parameters. Concurrent access patterns are not directly supported. Serialized access through locks is required for multi-threaded environments. A read-write lock interface is provided for scenarios allowing concurrent queries. Multiple simultaneous updates must be serialized. Copy-on-write semantics are available through explicit snapshot operations. Snapshots create independent tree instances at current state. Modifications to snapshots do not affect the original tree. Snapshot creation incurs overhead proportional to tree node count. Error handling returns specific error codes for invalid operations. Queries outside the initialized interval range return range error. Modifications to non-existent intervals return not found error. Serialization errors return format invalid errors. Stack overflow may occur with exceptionally deep trees during recursive operations. Iterative implementations are available through explicit algorithm selection. Memory allocation failures propagate to caller as allocation failed errors. All error conditions prevent partial state modifications. Performance characteristics scale logarithmically with tree depth for typical operations. Query time complexity is O log n, where n is leaf node count. Point update complexity is O log n. Range update with lazy propagation is O log n. Range update without lazy propagation is OK log n, where k is affected leaf count. Memory usage is On for n leaf nodes plus overhead for internal structure. Cache efficiency improves with contiguous allocation strategies. Debugging facilities include tree validation and integrity checking. Validation traverses the entire tree, verifying node relationships and aggregate correctness. Aggregate verification recomputes all parent values from children. Discrepancies indicate corruption or implementation errors. Detailed logging is available at trace level. Log output includes node addresses, values, and operation sequences. Debugger breakpoints may be set on operations affecting specific intervals. Memory inspection tools can visualize tree structure at any point. Usage examples demonstrate common patterns for interval aggregation. Building a tree for numeric range queries requires specifying min and max bounds. Summing intervals requires a summation reduction function. Finding maximum intervals requires a maximum reduction function. Range updates with lazy propagation improve performance for bulk modifications. Serialization workflows support checkpointing and recovery. Snapshot creation allows multi-version concurrency. The module integrates with standard collection interfaces for compatibility with existing code.